Have you ever felt a small electric shock when touching a doorknob after walking on a carpet? That's electric charge in motion. Until now, we've mostly studied charges at rest. But the real excitement begins when these charges start moving. That movement creates what we call electric current. Now, whenever a charge is placed in an electric field, it experiences a force. If the charge is free to move, it accelerates in response to that force. In some parts of nature, like the ionosphere, free charges are naturally present and can move. But in solids, especially metals, electrons are usually bound inside atoms unless the material allows them to escape. That's where conductors come in. In materials like copper or aluminum, some electrons become free to move within the solid. This is what makes them conductors. Let's remember the force formula here. We say F equals Q multiplied by E, where capital F is the force, small q is the charge, and capital E is the electric field. Let's take a closer look at metals. In materials like copper, the outer electrons of each atom are not tightly bound. These electrons break free and form a mobile cloud inside the metal. When we apply an electric field to this metal, the free electrons start to drift in the opposite direction of the field. Meanwhile, the positive metal ions remain fixed in place, forming the structure of the solid. So in metallic conductors, current is carried only by these drifting electrons. As shown in the diagram, we have a metal lattice of fixed positive ions, while free electrons move through it and carry current. This behavior is why metals like copper and aluminum are such excellent conductors of electricity. Not all conductors behave the same way. In solid conductors, such as copper wires, only electrons move. These electrons flow in the direction opposite to the applied electric field. But in electrolytic conductors, like salt water or acid solutions, both positive and negative ions move. That's how electric current flows in batteries. In semiconductors, we have electrons and what we call holes, which are effectively positive charge carriers. In gases, if the atoms become ionized, both electrons and ions can move and conduct current. In this lesson, we are only focusing on solid metallic conductors where the flow of electrons is responsible for electric current. Let's now consider a metal conductor with no electric field. Are electrons completely still? Not at all. Due to thermal energy, the electrons are constantly moving in all directions. But this movement is completely random. They bounce around and collide with fixed ions in the metal. Because the motion has no preferred direction, the total charge flow through any cross-section is zero. That means no electric current. As you can see in the visual, electrons move in zigzag paths, but they cancel each other's effect. So, there's no net flow. So, while electrons are moving constantly, they do not form a current unless there is a direction, and that direction comes from the electric field. Now let's see what happens when an electric field is applied. The electrons still move randomly due to thermal motion, but they also start drifting on average in a specific direction, opposite to the electric field. This average speed is called drift velocity, and it is denoted by V sub e. Here's the formula to calculate drift velocity. V sub a equals I divided by n times a times he. Let's break this down. V sub is the drift velocity, I is the current in amperes, n is the number of electrons per cubic meter, a is the cross-sectional area of the wire in square meters, he is the charge of one electron, which is approximately 1.6 into 10 to the power minus 19 coulombs. Even though drift velocity is very small, sometimes less than 1 millimeter per second, current appears instantly in a circuit. That's because the electric field spreads through the wire at nearly the speed of light. Let's calculate drift velocity with an example. Suppose a copper wire has a cross-sectional area of 1 mm squared and it carries a current of 3 amperes. The number density of free electrons in copper is approximately 8.5 into 10 to the power 28 per cubic meter. The charge of one electron is 1.6 into 10 to the power minus 19 coulombs. First, convert the area. 1 mm squared equals 1 into 10 to the power minus 6 square meters. Now, use the formula V sub A equals I divided by N times A times E. Plug in the values. V sub A equals 3 divided by open bracket 8.5 into 10 to the power 28 multiplied by 1 into 10 to the power minus 6 multiplied by 1.6 into 10 to the power minus 19 close bracket. Solving this gives V sub A is approximately 2.2 into 10 to the power minus 4 meters per second. That's a very small speed, but it's enough to create significant electric current because millions of electrons are moving simultaneously. Let's recap the key points about electric current in conductors. In a metal, electrons are always moving randomly due to heat, but this motion does not create current. When we apply an electric field, electrons gain a tiny drift velocity, symbolized by V sub A, opposite to the field. In solid conductors, only electrons carry current. The positive ions remain fixed. Although each electron moves slowly, the entire circuit responds quickly because the electric field travels almost instantly. We calculate drift velocity using the formula V sub A equals I divided by N times A times E. In the next lesson, we'll learn about Ohm's law, which beautifully connects current, voltage, and resistance in any conductor. See you in the next session.